Hello guys, welcome once more to another video in our YouTube channel. This is MAFA, which is Mathematics Academy for Africa on YouTube. So for those of you who are joining us for the first time, make sure you like the video, share the video with your friends, and you also subscribe to the channel. The comment section is open to you whenever you have a difficulty to ask. You can also get to me via WhatsApp using the number displayed to you on your screen. We are going to be looking at plane transformations today, and specifically we are going to talk about glide reflections. So without wasting much of your time, let's get started. Okay, so since I said we are going to be looking at glide reflections today, some of you might be wondering what glide reflections are all about. So from the name, we have glide and we have reflections. When something is gliding, it means it is moving from one place to another, and then when it is being reflected, I think you have a general picture of what is going to happen. So basically, glide reflections are the composition of two different transformations. We have a translation and then we have a reflection, specifically a line reflection. We otherwise call them orthogonal symmetries. So what we do is that we have to compose a translation alongside an orthogonal symmetry, but with the condition that the translation vector is parallel to the axis of the orthogonal symmetry, that is the line reflections axis. Alright, so again, to get a glide reflection, we have to do the composition of a translation with an orthogonal symmetry in such a way that the translation vector of the translation is in the same direction, that is parallel to the line reflections axis. Now let us picture this geometrically. What we do is that if we have a point M and we transform this point M, that is gliding, translating, we transform this point M to a point small m by a translation T whose vector is U. Here is a direction of my translation vector. Then later what I do is that I now have to reflect about an axis delta that is parallel to the translation vector. I reflect the point small m to get a point m prime about this axis. So the main thing is that your axis of symmetry must be in the same direction as your translation vector of the translation. So when this happens, the transformation involved is called a glide reflection. So we glide and we reflect, we glide and we reflect. So basically, theoretically, what we are saying is that if I compose an orthogonal symmetry whose axis is delta with a translation whose translation vector is U, and I want to find the image of a certain point M, what I do is that I first of all need to find the image of the point M under the translation with translation vector U, and according to what we have here, that image is the point small m. Then later I will now find the image of the point small m under the line reflection or under the orthogonal symmetry S whose axis is delta and it is parallel to the translation vector, and we are going to have m prime. Now this composition is commutative, which means that if I do the reverse composition, I will still get the same glide reflection. But if we do the reverse composition, which means that we start by reflecting, then we translate. So what we do is that we start by reflecting. We first of all find the image of capital M under the reflection, under the line reflection with axis delta, we get the point small m. Then later we now find the image of the point small m under the translation with translation vector U whose translation vector is parallel to the axis, we get the point m prime. So basically this is what we do. We reflect capital M to have small m, then we translate small m to have capital M prime. So the image of capital M in either ways is always M prime. Our small m is just an intermediary. Okay, so basically let us try to link the points, okay, and then we try to develop what this point is going to be. Then we try to look at an application exercise. Okay, so this point O here is the midpoint of the segment M prime M, all right, because that is the definition of a line reflection. If this transformation S of delta is a line reflection, then we have that if the point small m is taken to the point capital M prime, then the distance, the line capital M prime small m is perpendicular to the axis delta, and also the midpoint of the line segment capital M prime small m belongs to the axis delta, so that midpoint is O. Now by observation, this I here, the point I here, will definitely be the midpoint of the line segment capital M prime capital M. Let us prove that. Okay, so to be able to prove that, we are going to consider what we call similar figures. The triangle OM prime I is similar to the triangle M prime M capital M. All right, they have 90-degree angles. They are both right angle triangles, so basically the angles in them are congruent, so they are similar triangles. And for similar triangles, the ratio between their corresponding side length is always equal to a constant. In fact, the ratios of their corresponding side lengths are all the same. So since we have realized that these two triangles, because there's a 90-degree angle here, so the triangle OM prime I and the triangle small m prime capital M are similar triangles, so the ratio of their corresponding side lengths are the same. Now I'll begin with the side length M prime O. M prime O is just the adjacent of the triangle OM prime I. Now the adjacent of the triangle small m prime capital M is just the line segment M prime small m, that is the adjacent. Now this M prime I is the hypotenuse of the triangle OM prime I, and the hypotenuse of this other triangle is equal to M prime M. All right, now from here we know that this O is the midpoint of the line segment M prime small m. It definitely means that M prime capital M prime small m would just be 2 times M prime O, because this O is a midpoint. So I'm going to replace my capital M prime small m with 2 times M prime O. All right, and then from there you realize that M prime O can cancel, and at the end of the day I'll just cross multiply with the distance M prime M. I'm going to be left with half here, so you see that the distance from M prime to I is half of the distance from M prime to M. In other words, the distance from M prime to M is 2 times the distance from M prime to I. By definition, I is the midpoint of the line segment M prime M. Now on the diagram, the distance from, we have seen that M prime I is equal to half M prime M. So M prime I is equal to half M prime M. Therefore, I is basically the midpoint of the line segment M prime M. Alright, so that's our conclusion. I is the midpoint of the segment M prime or M prime M. Now let's look at an application exercise which we're actually going to solve in the next video, so make sure you stay tuned for the next video. So I'll just give the exercise, you try the exercise by yourself, then you now come to the next video and you watch the solution. So here is the exercise. Let F be a transformation that transforms every point M having coordinates x and y to the point M prime having coordinates x prime and y prime, such that x prime is y plus 1 and y prime is x plus 1. The question is, determine the characteristic elements of F. So basically in the next video I will show you guys and I'll explain to you guys why this analytic expression is actually the analytic expression of a glide reflection. And to find the characteristic elements of a glide reflection, we have to just find the translation vector of the translation and the axis of symmetry of the orthogonal symmetry that was composed with the translation to get the glide reflection. So stay tuned, and if you love the video, make sure you like the video, share the video with your friends, and you also subscribe to the channel. Thank you guys once more, and see you guys in the next video where we are going to be solving this application exercise.